Volumes are a gigantic part of Houdini and VFX in general. I would go as far as to say that around 90% of VFX shots require some use of volumes. And you might think that we as VFX artists only use volumes when creating explosions or smoke type of effects, but in reality volumes are used all of the time in many types of effects. This is why it's crucial to have a good understanding on what volumes are and how to use them. In Houdini, there are many ways to create and manipulate volumes, and we'll cover them more as we progress, but let's start with a simple volume. So I'll drop down a geometry container, let's step inside, and I will drop down a volume node. Now, we have a bunch of settings here, and I'll go over these in a second, but in order for us to see the volume, we need to give it some initial value. So in our first component here, we can set this value here to 1, and now Houdini will know how to draw this volume in the viewport. And this is the default behavior. As I increase this value here, we can thicken up this volume, and as I decrease this, we can fade it out. So if this reaches a value of 0 now, we won't be able to see this. This doesn't mean that the volume doesn't exist, just that it has a value of 0, so it's invisible in the viewport. Let's set this back to a value of 1, and we can also give this any name we want over here. Typically with smoke type of effects, you will often see the name density, like so. So this is what we'll use here. Again, you can give this whatever name you want. So whenever we are dealing with volumes, you have to think in terms of a 3D grid. What happens here is that we have this box, and if I go to my wireframe display and press W, we can see that this is the bounding box of our volume. And we can imagine cutting up this box on all of the sides. So let's press W again, and I'll just step in Photoshop for a second. I'll make a print screen of this. So let's say that this is our box, and I'll just create a simple outline of this. So if we slice up this box on all axes like so, and we divide this up, we are going to be left with a bunch of smaller cubes like this. And this small cube here is called a voxel. So each voxel is going to be this small box that contains information, and they're all going to be neatly aligned in this grid type structure. And how many voxels we have in total and how big this entire volume is can be determined by the settings over here. So we can increase the size overall, and if we increase the sampling divisions here, we can determine how many divisions we have for each side. So if I increase this, we increase the total number of voxels. And I'll set this for now, this uniform sampling method here, I'll set this to non-square just so we can better visualize this. Now we have a 10 by 10 by 10 grid, which gives us a total of 1000 voxels. So I can go to the information here, and we can see we have this 10, 10, and 10 here in between brackets, which specifies the size of our grid, and we have the total number of voxels here to 1000. In fact, if I'll just press D on my keyboard, and I'll go to the background settings here, and I'll make this background dark so we can visualize this better. And also in the guides tab over here, I will turn on draw time and also set the geometry information to always on, which will give us the total number of voxels in the corner of our screen over here. So we can see that we are working with 1000 voxels now. And if I increase the divisions here, let's try 100 by 100 and 100. Now we have 1 million voxels. And we can see how much sharper the volume got. Now we have this very crisp outline of our box. So there's a direct relationship between the total voxel count and the quality of the effects. Simply put, the more voxels you have, the better looking your effect is going to be. But this comes with an obvious drawback, which is that the more voxels you have, the heavier your scene gets. And this is another reason why Houdini is super powerful, because it can draw millions of voxels in the viewport very fast and efficiently. A lot faster than any other software at least. I can only assume that in Blender, if you want to use more than 5 voxels, it will crash instantly. So we can increase the voxel count here, and we can also have non-uniform voxels as well. So for example, if I grab this middle volume, so the count on the y-axis, if I set this to a value of 10, we will only have 10 voxels on this y direction, which means that the voxels will be stretched. So if I go back over here in Photoshop real quick, what happens is, let's maybe just disable this, a voxel will end up looking something like this. So it's going to be stretched out like so. So it's not going to be completely square. It's gonna end up looking like this, and voxels below it will look something like this. Now, with the settings that we use, this is going to be 10 times as stretched, but this is just to illustrate that we can have non-uniform voxels. This is not really super useful to have non-uniform voxels, but for some reason it's here, and we don't really have to worry about this. 99% of the time you will work with square voxels. So I will set this back to 100. Let's change this sampling mode here. Let's set this to by size, which is the version that you will most likely use 99% of the time. This 0.1 value is the result of dividing all the sides. So if I check the information here, let's also just set the size back here to a value of 1. So I will hold down Control and middle mouse click where it says size. So it's 1 by 1 by 1, just so we have nice and even divisions. So if I check the information here, we can see that we have this 10 by 10 by 10 grid. And if we divide all of these values, we end up with this size over here, 0.1, which is this size that we set directly inside the parameter. And now if we set this to a value of 0.01, we'll have a grid that's 10 times bigger on each side, and this will mean a total number of 1 million voxels. So we very quickly went from 1000 to 1 million, and this will mean that we have a grid that's 100 on each side. So again, if we divide all of these values up, we end up with a 0.01 value. Now there's a floating error here, we don't have to worry about this. We can safely say that it has this size of 0.01. So in essence, the lower value that you use over here, the more voxels we will get, and the better quality you will have on the effects. You will spend a lot of time adjusting these values, so you might as well get comfortable with using these low values. To better explain what a voxel is, I recreated the 3D voxel grid with actual geometry, just so we can better visualize this grid, and now we can also do some operations this way. So here I have a clip node that slices the geometry in half, and we can imagine now that this is a cross section of our volume, so these are the insides of all of our voxels. So each of these small cubes represents a voxel, and the information is stored right at the center of each voxel. So if a voxel has a density of 1, it's going to be 1 right in the center of the voxel, and if the voxel next to it is going to have a density of 0, everything in between is going to be smoothly interpolated. So a value that's halfway in between these two voxels will have a density of 0.5, and somewhere around maybe over here we will have a value of 0.75, so everything in between will be smoothly interpolated. And this is something we can have with any type of geometry or points or anything else. So this is why volumes are super powerful. And I created a simple visualizer here. I have my original volume that I created, and I just added some simple noise to it. And I have a sphere that I can grab now. And if I move the sphere around, I also have a text here that will read in the density of our volume depending on where our sphere is. So if I move the sphere around, we can see how our values change, and we can also see that there is a gradual and smooth transition between these values. Now, so far we have only been storing this density value, which is a float value, but we can also store vector values as well, which can tell smoke simulations or particle simulations in which way to go. And we'll get into vectors a little bit later, but for now I just wanted to mention this. We can have many types of data stored in voxels. We can also have integer values in matrices, but 99% of the time we are dealing with just the two types, float and vector values. In Houdini, there are two types of volumes, standard volumes and VDBs, and it's been decided a long time ago now that VDBs are the superior version, and I'll quickly explain why. If we have a geometry that we want to turn into a volume to later use in a smoke simulation, we can do this with an ISO offset node. So here it is, and I set the method here by size and set the division size of 0.025. Now, if I look at the information here, we are already working with roughly 500,000 voxels. And even though we see the density only where the geometry is, we in fact have voxels inside this entire bounding box of the geometry. So if I do a bound from here, this entire box is filled with voxels that store information. It's just that the voxels inside the geometry are 1 and all of the voxels outside are 0. And this is how Houdini knows how to draw this in the viewport. So again, I have a geometric representation of this 3D grid of voxels. And I will slice this in half to do a cross-section, and we can also preview our geometry as well. So this is basically the cross-section of the geometry too. So everything inside this bounding box is filled, and this is why we have this large number of voxels. So this is not ideal. So this is how the standard volumes work, and here we have the VDB version. So this is VDB from polygons. And if we compare these two results, we see we have mostly the same result with some minor differences, but the voxel size here is the same. So we are using the same size for our grid, the 0.025 value. So here we have the same value. And if I look at the information for our VDB versions, we see that we only have 57,000 voxels. So this is almost 10 times less voxels than our standard volume version. What happens if we do a cross-section of this? And let's also preview the geometry. We can see that we no longer fill up this entire bounding box with voxels, but only create them where we need them. And this is why VDBs are superior, because we can have what's called a sparse grid. So any voxel that would essentially have a value of 0 is removed from the grid entirely. This obviously saves up a lot of computation time and memories, so VDBs are a lot more efficient. And the cool part about VDBs is that they also come up with a lot of nodes. So if I press tab and type VDB, we can see that we can do really a lot of operations here. But what's cool is that we can also use all of the regular volume operations as well. So if I type volumes, we can use all of these nodes as well. So a VDB is still a volume at its core. So all of these other nodes will work as well. Whereas with a standard volume, we cannot use any of these VDB nodes. So if I were to go to my ISO offset version, I can't really append any VDB operations here because these won't work. So if you ever find yourself working on a simulation and you append a VDB node and it doesn't work, double check that you're working with a VDB volume and not a standard one. If I check the information for this ISO offset, we can see that our name here is with a teal color. So maybe I can also just give this a name real quick here. Okay, so we have density, and this is with this light blue or teal color. And if we go to the VDB version, if I check the information here, this will have a darker blue color. So this is just something to be mindful of. Now, to sum up, VDBs are very powerful and efficient, and moving forward, we are going to be using VDBs. With VDB comes another type of volume that's super important, which is called the Signed Distance Field, or SDF for short. Now, when I first started using Houdini and heard this name, Signed Distance Field, it sounded super sci-fi, like something out of Blade Runner, but in reality, it's pretty simple. To create an SDF, we can use the same VDB from polygons, and here we can say that instead of this fog VDB, we can turn this off, and we can turn on the distance VDB instead. So distance VDB will give us this SDF volume, which looks something like this in the viewport. And the way the SDF works is we have the same voxels that we had earlier with our density, so we are using the same size here. But the difference is that in each voxel now we are simply storing the distance from the surface of the geometry. So if I go back to the cross-section geometric representation here, and let's also grab our toy as well, and let's look at this. Let's maybe just do a slice of this so we don't have this entire half of the geometry on the side, and we're left with a thin slice. So I'll just do another clip here and reverse this and just increase the offset like so. And I'll repeat this for the geometry as well. You don't have to worry about all of these operations. Again, this will be just a geometric representation. So this is kind of what's happening if we were to grab a slice of our VDB. So if I zoom in here, I'll maybe do a print screen and let's step over in Photoshop. So here we have the surface of the geometry. And let's say maybe that this voxel here has a distance of, let's maybe say, for example, 0.1. Then this voxel next to it will have a distance of 0.2. And this one will have a distance of 0.3 and so forth. The further away we get, the higher our distance values will be. Now again, all of these values are interpolated, so we'll have information within this entire space over here. We also have information on the other side, so over here this voxel will have a distance value maybe of negative 0.2 and negative 0.3, and this is why it's called a signed distance field, because we have positive values on the outside and negative values on the inside. And in the viewport, Houdini will simply draw some geometry for each voxel where the distance value is 0. So this is why we have this kind of weird representation of our toy geometry. So this is what the SDF is, and we also have a couple of options here for exterior and interior band voxels. So by increasing these values, we determine how further out from the geometry we should have voxels. And this is better seen maybe in the geometric representation here. Let's maybe go to our clip, and I have set this up so that when I increase this peak node, we increase the narrow band. So if I increase this value here, we can kind of see what happens when I increase the exterior or interior band voxels. This is kind of what happens. We just add more rows of voxels on top of what we have. So if I go back to this, we can control each side individually, so how many voxels we have on the outside and how many we have on the inside. And using these values as they are here is directly related to the voxel size here. So the lower we set this size and the more voxels we have, the more we would have to increase our exterior band voxels. We can also use world space units instead. So when I turn this on, our narrow band will adjust accordingly to match the values that we set here. So now even if we change the voxel size for the entire volume, our exterior band size will be the same. So our expansion will be the same even as I increase this. We can see that the bounding box stays relatively the same. And this is useful a lot of the times because we can make tests on lower quality volumes for faster iterations, and then when we set the volumes back to a higher quality, we won't have to adjust these values as well. So this is all the SDF is. It's simply a volume that records the distance from the surface of a geometry, and this value can either be positive if it's on the outside and negative if it's on the inside. So we established that VDBs are preferred over the standard volumes, and a VDB can be a fog VDB or a distance VDB. And now we can start having some fun and introduce the volume VOP. So let's go ahead and add this. I'll type VV and I will go down here to this volume VOP. Let's drop this down and we will connect this with our VDB from polygons. And this volume VOP works on both fog VDB and distance VDB, but for now let's focus on the fog VDB. So over here, I'll turn off the distance VDB and turn on the fog VDB. So we will work on a fog volume first. Now, for this next part, it's important that you have previously watched the Intro to VOP series or that you know your way around VOPs in the context of regular geometry. A lot of things we do with VOPs or VEX for regular geometry can sort of be applied to volumes as well, and this is another big reason why Houdini is super powerful with volumes. And I just want to add the regular attribute VOP for now to compare the two. Right away, we can see a slight difference when we select either of these. The attribute VOP has the option to run over primitives, points, vertices, so all of the different components of a geometry, whereas the volume VOP doesn't have this option at all. So it's more unique than a regular attribute VOP. And if we step inside, we kind of have the same structure for the volume VOP as the attribute VOP. And in fact, I'll just do a screen grab of these so we can compare them side by side. So on the left over here, we have the volume VOP, and on the right, we have the attribute VOP. And the first difference that we can see here is that the volume VOP only has the one output, which is the density. And the attribute VOP has all of these different outputs because usually a geometry will contain multiple attributes. So we can export back to our position, velocity, force. And in the volume VOP, by default, we only have this density. Now, we can export to multiple fields as well, and we'll get to this in a second, but for now we can just focus on this density. For the inputs, we have some similarities as well. We have the position on both versions, and other than that, the only other things similar here really is going to be the time, timing, and frame. So we have this as well on the attribute VOP. And we have these four orange inputs over here, op input 1, 2, and 3, and 4. which will return the geometry that we grab from outside the volume VOP, so it's going to be corresponding with these 4 dots. So again, this goes back to everything we know from the Intro to VOP series. Now for the volume VOP, we also have these inputs here, IX, IY, ResX, center, orig. And to be honest here, most of these inputs, so everything that's between density and time, are not super helpful in most cases, and a lot of information that these inputs can provide, we can generate it ourselves from the position. So this P over here. For example, this BB stands for bounding box, and we can get the same thing if we were to append a relative to bounding box from our position here. And this node we have in the regular attribute VOP as well. So most operations inside a volume VOP, I prefer to do them using the position value, because this will be more consistent in the way that I do it with an attribute VOP when working with geometry. Now it's important to keep in mind that this position over here refers to the position of the voxel itself. So it's not tied to whatever information the voxel is holding, whether it's a density value or a velocity value. The position will give us where the center of each voxel is in our scene. So if I go up and if I go back to the cross section over here, I'll maybe zoom in here and we can do a screen grab of this. When we are inside a volume VOP and we are grabbing the position, we are really grabbing the center of each voxel. So we can imagine this point in the center of each of our voxels, and this will be what the position is referring to. So back in Houdini inside the volume VOP, it's important to keep in mind when we use this position that this is operating over the 3D grid of voxels itself, not really on the density values that are shown in the viewport. So let's maybe just set the display flag back to the volume VOP and let's start modifying this volume. So let's step back inside. One of the most common things you will do inside a volume VOP is use noise to break up the smoke. So from the position here, we can generate a noise pattern. Let's use a turbulent noise in this case. And if we plug the result of this noise inside the density, we can see our noise pattern over here. And now we can increase the amplitude and we can play around with the frequency and we can kind of see the results that we get. So again, this is just like how it would work on actual geometry. In fact, what I can do, I'll go up and from my rubber toy geometry over here, I'll just scatter a bunch of points. So let's drop down a scatter. I'll turn off some of these settings here and I'll just create a bunch of points here. Let's do 1 million. And if I append an attribute VOP, so the regular version, I can jump back inside the volume VOP with these settings that we set up over here. So I'll just grab this, Control C, and I can paste this inside the attribute VOP. Let's link this back to our position. And if I output this to my color, so inside the CD, we can see that we have the same pattern. So if I preview this and preview my volume, we have the same noise running over both of these objects. So this is pretty cool in my opinion, that you can just grab some of these nodes from the volume VOP and paste them directly inside an attribute VOP. So we can imagine that if we have a big network of nodes, you can grab all of them and you can just plug them inside an attribute VOP, and with some slight modifications you can do the same thing in both versions. Now if we go back to our volume and check our toy, we can kind of see that the toy has some sort of jagged border around it now, whereas before when we just had our density, so if I plug the density back inside our density, we can kind of see we have a way nicer and smoother border if we compare these two. So if I plug back the result of the noise, we have this ugly result around the border. And to get the correct result of this noise, we have to multiply it with our original density. So I'll plug the density back here and I'll drop down a multiply, and I want to multiply the existing density with our noise value. So if I apply this now, we have the smooth border that we had earlier, and we also have the noise pattern on top. So if I disable this, we can see the result, and we can also compare it with how it looks like if we just output the noise values, like so. So we can clearly see the difference now. And it's important to note that this noise and a lot of the operations that we do inside of VOPs operate on all of the voxels. And if I were to go up and I'll get rid of the scatter. I have the ISO offset node here, so again, this will mean that the entire bounding box is filled with voxels. If I were to duplicate my volume VOP node with the noise applied to it, let's plug this here and preview the result. If I step inside and if I output the noise values directly inside the density, we can see now that the entire grid is filled with this noise pattern. So our noise is overriding the values of all of the voxels. And this also goes back to what I said earlier about the difference between regular volumes and VDBs. Over here to the VDB, if we apply the noise directly, so if I apply this here, we don't fill up an entire box of voxels because the voxels only exist right outside the surface of the geometry. So all of this is to say that usually the operations we do in VOPs, we want to apply it to our existing density. So most of the things we do will either multiply, add or subtract from the original density and apply it back to the density or whatever other field we might have like velocity, temperature and so on. Let's set up a more practical example of VOPs, and this technique is something that I did in a lot of projects over the years. Let's just start with a fresh volume VOP, so I'll delete this one and I'll drop a new one, so volume VOP, and let's dive inside. Let's say that I want to fade the density along the height of our object, so I want more density at the base and no density right at the top. We'll drop down a relative to bounding box node and we'll connect the position to this node. And this node is covered in the Intro to VOP series, but just as a refresher, this node will give me a 0 to 1 value along each of the x, y, and z dimensions of our bounding box. And they're all stored as a vector inside this node. So if I want to grab the 0 to 1 value of our height, so the y-axis, I can do a vector to float from here, and this will split up the x, y, and z components. So if I want to grab the y component, this will be the middle value over here. So if I want, I can plug this directly inside the density. So let's plug this over here, and we can already see the sort of effect that we want. We have a gradient, only that this is starting with high density at the top and no density at the bottom, but we can kind of see this gradient here. Let's also remember that most operations, like I mentioned earlier, we'll have to do in relation to our existing density. So let's multiply this by our existing density. So I'll just plug our density back. I'll do a multiply here, and let's grab again the second value here, and this will be the new result. So when I plug this directly inside the density, we can see the difference. So we want to use the existing density here as well, and from here we can further add some more controls. So I'll make some room, and this 0 to 1 value of our y component, let's filter this through a ramp. So I'll grab the wire, I'll type ramp and choose this ramp parameter over here. I'll set the ramp type to a spline ramp, and now if I go up, we have our ramp controls here at the top, and I'll grab the endpoint here and just move this up, and now we have what we had previously, but I can reverse this ramp. If I click on this icon over here, we can do a complement ramp. So if I click this, now we have the reverse effect. So this is what we were aiming for. And now I can also control these handles to squeeze in the transition where this happens. So as I bring these handles closer together, we tighten up the region where the fading occurs. We can also offset this entire fading if I were to add or subtract to our position. So if I go back inside, over here before we introduce our ramp, so after this vector to float, I will do an add, and I will promote the second input to the top level. So middle mouse click, promote parameter, and if I click this, we can give this a name in the label region over here. So I'll name this offset, and now if I go up, we have this offset parameter here, and as I increase or decrease this, we can see that we are moving where this entire transition happens. So if I were to squeeze this even more together, so it's nice and tight, and if I move this around, we can essentially offset this transition. And hopefully we can see that already we are getting some cool results. So for example, we can animate this offset value to reveal our object like so. So really with just a couple of nodes, we're setting up some cool effects. And if I want to take this one step further, we can introduce some noise as well. So let's step back inside, and I want to displace the position from where we grab our bounding box values. So this P that we are plugging over here, let's go ahead and let's drop down an anti-aliased flow noise, and I'll drop this here. Let's generate this from our position, and this I want to be a 3D noise, and I want to add this to our position over here, again from where we generate the bounding box value. So let's drop down and add, and we will add our noise to this position, and we can already see this change in the viewport. So if I were to right click the noise and I go to the VEX VOPS options here, let's create input parameters. So this will expose all of the parameters that the noise has. Let's go up, and now here we can control the frequency of the noise, and we can control the amplitude, and I can go back to my ramp and I can fade this out less or more, and we can also control the offset of this. And one really cool thing that we can do here, if I animate any of the offset values, we can even introduce some animation in our noise. So for example, I can grab the middle value over here, which will be the offset on the Y direction for the noise. So we can see if I just scroll the values here, what this will do for us. So I can just simply set up an expression here that will tie it to our time in the timeline. So if I say $T, this will give us the time. And now if I play the animation, we can see in the viewport we have animated smoke, and this actually looks kind of like a simulation, but it's not really a simulation. We are just offsetting the noise. And if I want to make this slower, I can just divide this value here. So let's divide this, let's make this 4 times as slow. So I'll divide this with a value of 4. And if I play now, we can see we're starting to create a very simple ground fog. And this technique I used in a lot of projects over the years. So if, for example, I were to replace this geometry toy with a simple box, I can drop this here and I can just plug this directly in our chain, and we can see that everything updates. So I can press enter with the box selected. I will hold down shift and I can expand the dimensions of the box like so, and maybe I'll turn off the grid and press escape now. Let's go back over here, and to hide this wireframe, we can press Shift W, and now we can see we created a very simple ground fog, and this will work very well in a lot of cases. And you can see how fast and easy this was to set up. And because we are using the bounding box, this will work with any geometry. And for example, let's just do a pig head as well, and I'll plug this here so we can see that no matter what geometry are using or where it is in our scene, this will always work, because every object will have a bounding box that can contain it. So that's where the values are being generated, the 0 to 1 gradient values. So again, just to demonstrate this more, if I play around with the offset and I maybe play around with the ramp as well, or I can reverse this, we can kind of see the different results that we get. So a lot of cool stuff that we can do. I want to show one more practical example with density. So let's say that I want to fade the density from a specific position in our scene. Let's maybe just place this VOP to the side, and this can be, let's rename this to gradient fade, and I'll just create a new volume VOP, and let's rename this one to position fade. And if you want to grab these examples, I provide the project files with the downloads of this course. So if you're watching this on YouTube or some other place, I'll have the link to the course where you can download the HIP files so you can inspect the setups. Now, for this position fade, we'll want to reference a position in our scene, and for this, I'll just use a simple sphere. So I will drop down a sphere and I will set this to a primitive. So if I use this primitive option, this sphere will be treated as one single point. So I can go to the information tab and see that we only have 1 point. And this is just so we can easily reference this as point 0. Let's also append a transform to this sphere so we can move it easily in our viewport, and maybe I'll move it to the side. Let's template our pig head geometry to see where it kind of is. All right, so I think something like this will be fine. I might want to make this sphere smaller just for preview purposes. It doesn't really matter what scale this is, but I'll just make this smaller. So after this transform, let's plug this in our second input of our volume VOP. So now if we step inside, here we can do an import point attribute, and we will use this to grab the position of our sphere. So the attribute will be P and the signature will be vector3, so this is fine. The input we want to point to our second input over here, so let's dive back. So we will point this input to our second input, and we also have to specify the point number. And again, since we are using just one point, the point number will be 0, so I can middle mouse click this ptnum value here and promote this to a constant, and I will leave this with the default value of 0. So now with our sphere position, we can generate a distance from this sphere to the position of each voxel. So we will grab the voxel position from over here, we'll do a distance, and we'll plug the sphere position as our second input. And if I plug this directly inside the density, we see something sort of happening. And by default, the distance values as they are will not be super helpful. So we have to remap these values. We can use a fit range after our distance. And with the source min and max, I can control the spreading of our fading. And we can kind of see something happening here around the ear. As I move this source max value further out and I increase this, we sort of start to see this gradient effect. And I can reverse the destination min and max to reverse this gradient. So if I set this here to 1 and our max value to 0, now we can see this gradient a lot better. Of course, we will want to multiply this with our original density. So let's plug the density back. We'll do a multiply and let's plug the fit result in our second input. So let's maybe just promote the values of the fit. So I'll go to Vex VOPS options and let's create input parameters. Let's go up, and now if I grab the transform of our sphere and press enter, I can move this around and I can determine where I want this gradient to originate from. So this is very helpful a lot of the times. Let's maybe just reverse the values here back to where it was originally. So let's say that in our 3D space, this position where our sphere is, let's say that this is our camera, and I want to fade the density that's closest to our camera, because a lot of the times what happens is when you have a volume simulation that comes towards the camera, so you can imagine something like a dust shockwave, you might not want the density to obscure part that's right in front of the camera too much. So you can grab the camera position and you can fade the density that's closest to the camera like so. So if I if I just place this over next to the ear, we can see the effect that we are having. So this is super useful a lot of the times, and I use this in a lot of other projects as well. So this is just another practical example of what you can do with a volume VOP. Now, like I said, a lot of the operations that you can do with a regular attribute VOP, you can replicate in a volume VOP. And really here we're just scratching the surface of what's possible, and we can really push this a lot. So in my Magical Skybeam course, we use volume VOPs to modify the cloudscape, and the animation of the cloud spreading apart and twisting is also done with volume VOPs. So we can use VOPs to fake simulations, create interesting volumes, and we can also layer them on top of real simulations to get that extra level of control. And if you want to check out this course, this will be available on my website, voxsite.com, so feel free to check this out. Now, so far we've only been doing operations over one volume, which was our density, but we can actually store multiple values in the same object. So in fire simulations, you will usually need a volume that drives the flame and a separate volume that drives the smoke that the flame creates. So having multiple volumes is important for the simulation process, but also for rendering. We usually need different settings to control the flame and the smoke separately. We'll start fresh with a rubber toy and we'll do a VDB from polygons, and let's turn this into a fog VDB, and I'll decrease the resolution here, or rather increase the resolution by reducing the scale, so I'll use 0.01. Now if I do a volume VOP from here, so far we've been affecting our density. So in between here, if I do, for example, a multiply constant, I can increase or decrease the amount of density we have, and everything works. Now, this output here is set by default to export to a volume that's called density. So in our VDB from polygons, if I go up and I go back here, if I change the name here to, let's say, temperature, now we can see that this volume VOP no longer works. So if I go back inside and modify our values here, nothing changes. In order to affect this volume that's now called temperature, we have to do a bind export and we have to specify the name ourselves. So in the name parameter here, let's type temperature, and I will also need to bring in the temperature volume. So I will do a bind, so regular bind, not a bind export. Let's do a bind. Let's also name this to temperature. I'll plug this input temperature to our output temperature, and if I just duplicate this multiply constant node here and plug this in between, now we can see that this works. It's still represented as a fog in our volume, but we can see that now we can affect the temperature volume. So if I go up, we have to be mindful of the name of the volume that we are operating on. So this bind export kind of works in the same way it does in an attribute VOP, where we can bring in and export attributes on geometry, but the difference for volumes is that we can't use this bind export to create new volumes. The volume has to already exist in order to do operations with it. So for example, if I go up and if I were to be working on a standard geometry, so not a volume, if I do an attribute VOP from here, I can grab any of our input attributes that we have and we can do a bind export. So let's grab our position, for example. I'll do a bind export and I'll name this to pos. Now if I go in the geometry spreadsheet, let's hide all attributes and let's only show our pos. We have this pos attribute, and if for example I grab the same position and let's just modify this for example's sake, I'll do an add constant here and just add a value on all axes. I can do another bind export like so, and let's just name this new pos, for example, and we can see we have created a new attribute with both the bind export. So now we can see the new pos attribute here as well. Now in a volume VOP, let's also go back to the scene view. We can't really do the same thing. We can't do a bind export and create new volume. So for example, if I want to create a new volume based on temperature, let's do a bind export and see what happens. So I'll do this bind export and let's name this to heat. Nothing changes, and if I also go up and I look at the information, we still only have the temperature field created. So our heat field that we want to do operations on has to already exist. And for example, I can duplicate our VDB from polygons node. If I hold down Alt, I'll just duplicate, and this new volume, let's name this one heat, and now I can merge these two together. So I'll drop down a merge. Let's plug our second VDB from polygon here, and now we can kind of see something happening in our viewport. If I look at the merge information here, we have both fields that we need now, temperature and heat, and now in our volume VOP, we can affect this heat field. So if I do a multiply constant here, and if I play around with the settings, we can see changes in our viewport. So we are indeed affecting our heat field. It's just that both the temperature field and the heat field are displayed as fog in our viewports, so we don't really have a clear visual indication how this works, and we'll talk more about this in a second. But for now, I just wanted to express that unlike the bind export in an attribute VOP, in a volume VOP, the field needs to be there already in order to do operations on it. So let's go up and I'll get rid of this volume VOP and also the attribute VOP. And like I said earlier, in a typical fire simulation, we will have a field for smoke and a separate field for fire. So I'll name one of these fields, let's name this density. And for the second VDB from polygons, let's name this other field temperature. And you can use whatever name you want here. It's just that a lot of the nodes and presets that Houdini comes with will look for these names by default, so temperature and density. And this is why I'm giving them these names. And now when we merge the two volumes, we have both fields here, and we can change the resolution for each field individually. But sometimes you will want to create a volume volume based on an existing volume in order to have the same resolution. So let's go ahead and get rid of the merge and the second VDB from polygons. And let's say that I want to base the temperature off of this density field. I'll set the voxel size here back to 0.01. And to create our temperature field, I can simply change the name of this volume. So I can append a name SOP here, and I can set the name here to temperature. And now we can see that this name changed here from density, and I can simply merge this back together with our density. So we have the same result now, temperature and density, but now with this VDB from polygons, I will control the resolution for both fields at the same time. Now we are drawing both fields as smoke in our viewport, but let's say I want to use the temperature to control the emission of the volume. To do this, we can use a volume visualization node. So let's append this here. In this node, we will have two tabs, one for smoke and one for emission, and we can specify which fields we want to drive each of these. So for smoke, we are looking for our density field by default here. So I can use this ramp here to remap our values, and we can kind of see something happening in our viewport. Let's maybe break up the smoke, so introduce some noise in order for this to be more obvious. So after the VDB from polygons, I want to do a volume noise fog from here. And this node is really just sort of like a preset of what we built earlier ourselves with VOPS. So over here, I'll set the operation to multiply. Let's do zero-centered range values. And I'll also enable ramp, remap ramp here, and I'll just bring this point up slightly. So we can see we have the same result that we had earlier. So again, all of this we can do ourselves in a VOP node. And if I press tab and type here volume, we can see we have a lot of operations that do different things. And a lot of these are based on volume VOPs. So in fact, if I were to go inside this node, so right click and allow editing of contents and step inside, we can see that it's really just a volume VOP at its core. And this is why I'm stressing over this volume VOP so much. If we understand how the VOP node works, we can really do anything we want, and we're not limited to these preset options that we have here. So going back to our volume visualization node, if I adjust this ramp now, we can see how we can affect the density in our viewport. We can also multiply the density scale overall to thicken up our smoke, but it's important to know that these changes are only affecting our viewport display. We are not really modifying the actual density values stored inside the voxels. We are just artificially changing the values as they are displayed in the viewport. This is important because when we render, we'll have to do the same thing. The density values we use here, we can also use later in our shader when we do rendering. And with this volume visualization node, we can get an idea ahead of time of how it's going to look. We can also give our smoke a different color, so we can map this diffuse field to a different volume. But a lot of the times we'll use the same density field, so let's just point this to the density. And now if I change this ramp here, we can see how this affects our smoke. So I can give this a blue color. I can play around with the remap values here, increase the density. So this will be our smoke. And in the emission tab, we can point the emission field here to our temperature. And now if I increase the emission scale, we start to see something happening. Usually with the emission, we will have to use values above 1. So I'll just use 10 in this case. We can also remap the ranges like we did for our density with this ramp. And we also have a color field, which we can use a different field, or we can point this to the same temperature field. So if I set this to temperature, we can kind of start to have this fiery look. And this is because by default, Houdini gives us this orangey ramp that's giving us a fire look. But of course, we can change this if we want. So I can use a different color here. And when you are setting the colors for the emission, it's important that you introduce a bit of white to the colors so it's not completely saturated. So I'll just reduce this here to a saturation maybe of 0.9. And if I go back to the emission scale here, I can increase this further to make this really bright, play around with the emission ramp, and we can maybe also introduce more color information here. So I might want to drop this down slightly to have more of a gradient. And if I increase the whiteness point here, I can also remap the minimum and maximum ranges we are sourcing. So if I turn this on and I reduce the maximum range, we can see we are starting to introduce more of our end color here. So if this were more white, we have this very vivid gradient now. So we really have a lot of visualization options here. Now, currently our temperature field is the exact same as our density field. So these two are overlaid exactly on top of each other, and we can't really tell apart the density from the smoke. So we can add a volume VOP before our volume visualization. So let's drop a volume VOP down and let's step inside. And let's do some changes only on our temperature field. So I will do a bind and let's bring in our temperature. And we will do the same thing as we did earlier with our gradient fade along the bounding box. So from the position here, let's do a relative to bounding box. Let's split this vector up. So let's do a vector to float and let's go ahead. Let's grab our temperature. I will do a bind export back to our temperature. So let's type the name here. I'll plug these together and let's also, so from our second input, which will be our height, let's also use a ramp so we can further control this, and I'll set this to a spline ramp. And now we want to multiply our existing temperature by this ramp value. So let's plug this over here, and if I go up, I can reset the ramp. So I can hold down Control and middle mouse click the title here. This will give us the default ramp. And now if I go back to the volume visualization node, let's maybe increase the emission scale. We can kind of see something happening, and let's maybe just set this back, our emission ramp, to the default values. I can go back in this volume VOP, and if I reverse this ramp now by clicking this button here, we can see what's happening a little bit better, and I can squeeze this ramp now to determine where we want our emission field. So we can see only the base of our rubber toy has this emission, and if I go back here, let's maybe just go to the smoke, or let's maybe just rather increase the density. So I can push this out further to increase the density, and let's maybe just use the default colors for our ramp for the density. So I'll reset this diffuse ramp just so we have color only on the emission. And this is now the result. So if I go back to the emission, let's maybe turn on the emission color ramp back, and I can increase the emission scale even further, and we can see how the emission is only here at the bottom. Maybe I can go back to the volume noise fog and change these settings a bit, and hopefully you can see now where I'm going with this. I can go back to the volume VOP here and control where our emission starts to fade, and we can clearly see a distinction now between the density field and the temperature field. An even cooler thing we can do here, instead of this volume noise fog, we can drop down a cloud noise, and let's replace the volume noise fog. So I'll get rid of this and I'll plug the VDB from polygons into this cloud noise, and let's plug these inside our cloud noise like so. So we can see what this happens. And if I just look at this cloud noise, this will simply displace our volume in sort of like this cloud shape, and we can adjust the settings here if we want. We can make this more obvious and increase the element size and so on. So all of these settings are pretty self-explanatory. And if I step inside this cloud noise, so I choose allow editing of contents and go inside, you can probably already guess that this is also based on a volume node. And in fact, if I step inside here, we can see the entire network that creates this effect. Now, this is really a huge network, and this is because Houdini wanted to give us as many options as possible, but really the logic behind this effect is a lot more simpler than this. To recreate this, we only really need a few nodes here. So you can actually check out how this cloud noise is built. So let's go up and let's go back. And if I look at the volume visualization now, we can really start to see some cool effects. Let's maybe just set our emission ramp. So in the emission tab, let's set this back to our fiery look. So now we kind of have this fiery look on our rubber toy. And I can go back to our cloud noise and I can even animate this, and we can create some really cool effects. We can also use a more advanced version of this volume visualization node, and this was introduced more recently in Houdini. We can drop down a pyro bake volume, and here we have a few tabs The smoke tab works kind of the same as it works in the volume visualization tab, so I can increase the density of our smoke like so. And if I go to the fire tab and turn this on, we kind of have the same thing as we did with our emission, but we also have this scatter tabs. So I'll just turn off the fire for now and turn on the scatter one. So if I turn this on, we start to see something happening here. And as I increase the intensity here, let's increase this a lot more. And maybe we can just reduce the source range. So if I decrease this value here, we can start to see our scatter a lot better. Let's maybe increase this even more. And the values here are kind of directly related with our smoke. So I can decrease the density scale to make our scatter more obvious. Let's maybe increase the shadow density as well and make our smoke darker. And let's go back to our scatter tab and we can play around with the settings until we get something really cool. So we can play around with some of the blur values and the masking as well. So this scatter is used all the time in explosion to get this fine detail that's using the density field as a mask on the temperature field. And we can kind of see how we get this sort of pyroclastic look. And maybe I can go back to our volume VOP here and let's make some changes on this ramp. Let's maybe use another dot here and I'll make this a B-spline so we have a smooth fading. And also I can increase the temperature values directly inside the volume VOP. So before our pyrobake node, if I go inside here, I can simply grab the third value here of our multiply and I can promote this to a parameter. And if I rename this to, let's say, global amount, if I go up and I increase the global amount, we will multiply everything that's happening after our volume VOP. So if I increase this, we can kind of see how everything else increases as well. And maybe I can also, in the pyrobake volume, maybe I can increase the hot core a little bit, maybe not so much. So we can see that this does take a little bit of fine tuning, but we can get some really sick results. We can also add the fire on top of this. So if I add the fire back, we also have our original emission on top. So maybe I can reduce this. So we really have a lot of options here to control this look, and we can see how easy it is to get a pretty cool effect. We can also use volume VOPs on distant VDBs, so SDFs. Let's drop down another VDB from polygons here, and we'll use the default distance VDB here. So this will create an SDF that's called surface, and let's maybe just decrease the voxel size here, so increase the resolution 0.01. And let's do from here a volume VOP, and let's step inside. So again, we right away run into the same problem with the naming, which is that this volume VOP is tied to density and we want to bring in our surface field. So let's do a bind. I will type here for name surface. And if I hold down Alt and duplicate this node as it is, I can turn on this option to use this node to set parameter attributes, and the export here I will type to always, and this essentially now turns it into a bind export node. So if I do a bind export, we can see that this is the same node as a bind with just different settings to it. So this is how we can recreate the bind export node. So now if I plug the surface input into our output surface, in between here we can modify our volume, and if we do a multiply constant and I increase and decrease this value, we can see that nothing happens, whereas on a fog volume this will fade out our density or thicken the density, but nothing happens for our SDF. And this is usually because with SDFs we want to add or subtract values rather than multiply or divide. So if I instead delete this and add a add constant node, now if I set this value to 0 here and I slightly increase the value, we can see we push the SDF in, and if I decrease this value, push the SDF out. And this is already different than if we were to add or subtract values from a fog VDB. So let's go back to our cross section and see exactly what happens. Let's go over here and also template the geometry, and I'll just step inside Photoshop real quick. So right over here is where the surface of our SDF is drawn, meaning that right on the surface this voxel will have a value of 0 over here, and over here we'll have 0.1, and further out we'll just increase the density, so maybe this is 0.2, and here we'll have negative 0.1 and negative 0.2 and so on. So when we add or subtract values in a volume VOP, this operates over all of the voxels at the same time. And this voxel over here where we have negative 0.1, if we add a positive value, so if we add 0.1 to this now becomes a value of 0, and so our surface will be drawn over here. And this is why when we add to our SDF, we are actually pushing the volume in. And similarly, when we subtract a value of 0.1, so if we subtract it from over here, now this voxel will have a value of 0, and our surface will be drawn further out over here. And this is more or less how we can think about SDFs as operations that are pushing and pulling along the normals of the volume, like so. So it's kind of like pushing the normals of the geometry. So if I grab the rubber toy and I add a peak node to this will push the points along the normal. So if I increase or decrease this, we kind of have the same thing happening as with our volume VOP on the SDF. So if I go inside here, let's maybe just delete this and do another add node, and I'll just promote this to the top, and I'll rename this label here to add. So if I increase this, we push our volume in, and as I decrease this, we push the volume out. Only the problem when we do it on the geometry, we can see that the geometry starts to intersect with itself, and we get this very weird and nasty result, whereas with our SDFs, we don't have this problem because everything will be smoothly interpolated, since that's the nature of volumes. Now, if I push the values slightly more, we can see that the SDF suddenly starts to disappear. Now, going back to our cross-section, and I zoom out here a little bit, even though we are offsetting the values and we are pushing the surface out like so, we are still operating within the same voxels with which we start. So when the surface that we push out reaches outside of the volumes that we have, so for example over here, we can no longer draw our surface in the viewport because those voxels here don't exist. And this is where on our VDB from polygons, our exterior band and interior band voxels come into play. As I increase these values here, we start to introduce more voxels around our mesh, and now we are able to push our volumes more. We can still see that we reach the limits of our voxels, and for example, we have this very handy option here that says fill interior. So now everything inside our mesh will be filled with voxels. So now essentially I can push this in as far as I want because we have voxels everywhere inside our mesh. And we can see how easily, if I were to animate this value, we can create a revealing geometry animation like so. And to turn this SDF into regular geometry, we can do a convert to VDB from here. Let's append this to our volume VOP and let's convert to polygons. And now if I press Shift W, we have actual geometry. And we can play around with the adaptivity size over here. So if I increase this, this sort of decimates the geometry and tries to retain the shape. And if this is a value of 0, it's going to use the maximum subdivisions that it can. And the resolution of this geometry is tied to our size of our VDB. So if I decrease this voxel size here, we are also going to decrease the resolution of the geometry. So these are tightly linked together. Some of the other advantages of SDFs is that we have a lot of algorithms pre-built to help us change the shape. So for example, after the volume VOP, we can do a VDB smooth SDF, and we can kind of blur our result. I can increase the settings here and try different operations and see what we get. And the VDB smooth here is used in a lot of different effects, and it's also used to help us with meshing fluid particle simulations. Also, a very common one is going to be VDB reshape SDF. And if the operation here is dilate and I push this out, we kind of have the same result as we do when we simply add to our SDF, so as we did earlier with our volume over here. Only with the VDB reshape SDF we have some extra options here, so we can control this a little bit better. And if I type SDF here, we can see that we have a few more operations that we can do. So these are all pretty helpful, but the VDB smooth and the VDB reshape SDF are two of the most commonly used nodes. So I'll get rid of these three nodes and let's go back to our volume VOP. and I'll reduce this end node. In fact, let's go inside and let's remove this promoted parameter over here. And instead of adding a constant value to the SDF, we can generate noise values and add those instead. So from our position, we actually don't need this volume VOP node. We can get rid of this. I'll get rid of this global output here. And let's just grab our position, so the P, and we'll do a turbulent noise. And we can plug the values of this noise directly inside our add. And we can kind of see something happening. Now, to further control this, we can do a fit range after our turbulent noise to further control our values. And I can decrease the destination max now. And we can see that as I increase this, we start to eat away more of our SDF. And we also have this nice noise pattern. We can also go to the turbulent noise, and I'll set the type here to simplex. And I know that the simplex outputs values between -0.5 and +0.5. So in our fit range, I will set the source min to -0.5, and our source max, let's do 0.5. And now we can use the destination min and max values here to sort of push in our SDF if I increase the destination max, and I can also push out some values if I decrease the destination min here. So I can go in the negative direction, and we can see how some of these values now inflate sort of our rubber toy. So we can control these both, and we can get some interesting results. And of course, we can go to our turbulent noise and increase the amplitude. So this will accentuate the difference between the low and high values. And I can also play around with the frequency and the roughness. So we can get a lot of interesting results. And we can turn this into geometry now if we want to. And we can really build a lot of organic shapes this way. Now, it's important to know that even though we are displacing the SDF in 3D, the noise values that we generate here are 1D. So this signature here is a 1D noise, and this is outputting a float value. And this is something to keep in mind while working with SDFs. Usually you will want to add or subtract float values, whether you generate the values with noise or something else. If I change this signature to a 3D noise, we still get something going, but this is not super helpful as we are adding a vector to what's essentially a scalar field. And we'll get more into this a bit later, but if we go back to what I said earlier, an SDF contains a distance value from the surface, and this is a float value, so it doesn't make sense to add a vector to it. And for example, if I go up and if I were to do a noise displacement on the regular geometry, so from here I'll drop down an attribute VOP. Let's go inside and I'll plug our P into the output P, and I can generate a turbulent noise here. If I set this to a 3D noise and add this to our position, so let's go ahead and add the noise here. And let's also do a simplex so we have both directions. So I'll set this to simplex noise and maybe increase the frequency. And we also need to update the normal, so I'll go up and I'll just append a normal SOP as well, just so we have the correct shading. Let's go back inside the attribute VOP. With this amplitude, we can control the displacement, and we can see that this works fine when we are using a 3D noise to displace the geometry, because we can move the points around in 3D space. But again, with volumes, we can't really move the voxels. We can only change the values that the voxels contain. And if I wanted to kind of replicate on the geometry what happens in an SDF, we can use a displace along normal node. So I'll drop this here. Let's get rid of this connection. And I'll go back to the turbulent noise and set this to a 1D noise and plug this in the amount input over here. And now I can plug the displace P in our output position. So now if I go to this displacement, I can increase the scale, and we can kind of see we are pushing the geometry along their normals. So this is more on the lines of what's happening with an SDF as well. But we can see the limitations when we are working with regular geometry. We have all of this really nasty intersection, and we are really depending on the geometry resolution. Whereas with a volume VOPs, we no longer have these problems, and we get a smooth interpolation between the voxels, so we get an overall much smoother result, and we don't have any intersecting problems. So in our volume VOP, I'll go back here and let's set this signature to a 1D noise. So it's important with SDFs to always keep in mind that even though we are displacing this volume in 3D, we are in fact working with float values. So there's really a lot of applications with SDFs, and they're commonly used to create all types of shapes and geometry. And for example, I'll start with a simple sphere. So let's drop this down. I'll set this to polygon and increase the frequency. And also I might increase the uniform radius, or rather uniform scale here, to a value of 2. And let's turn this into an SDF. So we'll do VDB from polygons. We'll keep this as surface. I might want to increase the resolution, so let's do 0.05, and let's append a volume VOP here. Let's step inside and we'll do a bind on our surface. So again, the same process that we did earlier. I'll set the name here to surface. I'll duplicate this node by holding Alt. And on this node, I'll turn on use this node to set parameter and export to always and plug this here. So earlier we used a noise pattern to displace this SDF, but Houdini really comes with a lot of different patterns that we can use. So let's get rid of this density here, and from my position, let's do a cellular noise. So this comes with all kinds of different parameters and even outputs. Let's just see if we add one of these outputs to our surface, and if I grab the border here and add this, we can kind of see an interesting shape in our viewport. Usually with any kind of pattern for SDFs, you will want to pair it with a fit range node. So let's drop this here, and I'll just decrease this destination max for now, and let's see what happens. We are lacking some voxel information when we go inside our volume here, so let's go up and let's go to our VDB from polygons and turn on our fill interior option, so we don't get this volume disappearing when we push our volume too much inside. And also I might decrease this voxel size. Let's use 0.02 so we get a higher resolution. Let's go back inside, and now if I increase the destination max, we can push this further in. And if I were to go up, I can convert this. Let's do a convert VDB, and let's plug this here, and I can turn this into an actual geometry. So now we also have polygons. And like I said, we can use all kinds of patterns that Houdini provides to create a lot of interesting shapes. So this is already looking like a sci-fi spaceship or something. Let's go back inside here, and we can also play around with the source min and source max and see what different results we get. So maybe I can reduce the source max, or I can push the destination min out. And we can see that we also need some more voxels on the exterior of our surface. So I can go up, go back to this VDB node, and I can increase the exterior band voxels. So when I increase this, we can add more until we no longer have these holes in our VDB. So we can see with a high enough value, this fixes it. And this is also why I like to use the world space units instead. So if I turn this on, we can set this to a value directly here. So we can see that if I set this exterior band to a value of 1, if we look from -3 to -4 over here, this is the entire 1 unit length that the SDF, or rather our voxels, will cover. So we really have a lot more room now. And I think the world space units is a little bit more intuitive. So let's go back inside, and let's maybe choose one of these other outputs for the cellular noise. Let's try distance 1, and we can see what kind of weird results we are starting to get over here. Maybe I can play around with the values and get something kind of interesting going. So feel free to play around with some of these patterns. There's also a pattern for hexagons. So if I do a tiled hexagons pattern from here, we have to pair up our ID with a random node. So this will give us a random value per each hexagon, and we'll see this in a second. If I plug the result of this random inside the fit range, we can kind of see what we get over here. And again, in our fit range node, I can play around with the settings here. So we can also use this to create some interesting patterns. So this looks pretty interesting as well. With a lot of these patterns, let's get rid of our cell noise. With a lot of these pre-built patterns, we can displace them if we displace the position from where we generate the pattern. So if we do a turbulent noise from here, I want to set the signature here to a 3D noise, and let's use simplex, and we will add this to our position over here. So let's do an add, and let's plug our noise here. And now this will combine our hexagon pattern with this noise. So if I drop down the amplitude here, we can control how much noise we introduce. So now we can really start having some fun with this SDF. And we can see right away that we can kind of use this to create some really interesting cracks on a ground surface. We also have a Voronoi noise. So if I drop down the Voronoi noise, it kind of works in the same way. We can plug our position in the position here, and I'll grab this seed and plug this inside the random. And now we have a Voronoi pattern. So if I increase the frequency here, maybe we can see this better. And of course, we can go back to our feet range and let's try some of these values out. Maybe I can push in our source mean, or I can push this out or inwards. And this will take a while to get used to. We can also layer these patterns as well. So for example, I can duplicate these nodes and let's plug this ID from our hex tile back inside the random, and I can add our hexagon pattern on top of what we have also. So when we do this, we really start to get a lot of interesting and organic shapes, and we can see how easily it is to layer stuff and get super complex geometry. And one classic example of an SDF is to create some simple rocks. So I'll get rid of all of these nodes. Let's go back here, and I want to generate a whirly noise for this. So let's drop down a whirly noise. We'll grab our distance 1 output. Let's do a feet range. Let's plug this in our add. And for the whirly noise, I will decrease the frequency here. And if I go to the feet range, I can reduce the source max and the destination max. And actually, maybe I want to increase the source mean. I'll set the source max to 0 and increase the source mean. And we can see we get this faceted result that kind of looks like a rock. So now I can increase the destination max, and we end up with a really cool looking rock, or at least a base for a rock. And of course we can still displace our whirly noise pattern with, again, if I use a turbulent noise, set this to 3D noise, and let's maybe just use something else. We can also use sparse convolution noise here. If I do an add and displace this position before we input it in our whirly noise, so let's plug the noise to our add. We can see now that this is actually really starting to look like a rock. So maybe I can decrease the amplitude here, and here we have it. So now if I go back to the whirly noise, I can play around with the offset here, and if I change the offset, we see how fast we can generate an infinite amount of rocks this way. So really powerful and useful stuff. Like I said, SDFs are used to create all sorts of organic shapes and even some hard surface shapes as well. Now let's do one more practical example, and for this I'll go back to my rubber toy. Let's just duplicate this over and I'll copy these nodes, or rather switch the sphere to my rubber toy. So let's go to our settings here. I might reduce the voxel size to increase the resolution, and if we go inside the volume VOP, let's go back here, and I want to keep the bind import and the export, and I'll delete all of these other nodes in between, and let's just delete the add for now. And let's do the same trick that we did with our fog, which was the gradient based on a bounding box. So let's do from our position, we'll do a relative to bounding box. Let's split this vector up, let's do vector to float, and let's use the z direction instead, which will be our third value here. And if we plug our z value here inside a compare node, we can set this condition here to greater than. So now all voxels that will have a bounding box value on the z direction greater than the amount we set here will retain the current SDF values, and if this condition is not met, we are going to set the surface value to 0. So if I just simply add this compare result to our surface, if I do an add here and I plug this here, now as I increase this value, we can kind of see we have this reveal of our object on our x direction. So this is something pretty cool. And here as well, if we want to introduce some noise, we can introduce it before our relative to bounding box. So we can do a turbulent noise from our position. Again, I'll set this to a 3D noise and we'll do simplex. Let's add this here before the relative to bounding box. And now we have some noise as well. And if we convert this back to geometry to preview this better, let's do a VDB convert from here, and let's set the convert to polygons. Here we can see the result, and if I go back inside, we can control this transition with this compare value here, so I can push these values around to reveal our object. Now in reality, when we set this to a value of 0 here, this is where our transition should start, but we can see that we have to go quite high here in this value, so maybe at around let's see, at around 0.3 we start to reveal our object, and this is because the bounding box is based on the voxel. So if we go up to our VDB from polygons, we have a lot of extra voxels around our surface. So if I press Shift W, we can see that this is actually the bounding box, and this is because we set this exterior band here to a high value. If I reduce this, we can start to see that we get rid of some of these voxels, so now all of our operations will be faster, and our bounding box also will better match our object. So I can reduce this quite a bit here, and now if I go back to the convert result, if I step inside the volume VOP, now we can see that as I get closer to a value of 0, we actually start to reveal our object. We still have a little bit of a gap, but it's not as big as before. So now if I increase this from around 0, we can go all the way up to a value that's close to 1, and this way we reveal the entire object like so. So this again can be the grounds for a lot of different effects. And in my laser reveal course, we used a similar technique to sort of grow the helmet, only in that case we layered more stuff with our SDF to create a more complex look. Now, so far we've been dealing with these two types of volumes, distance VDB and fog VDB, and these can store float values. So here again, this is the cross-section of our rubber toy with some voxels surrounding it, and this here, this blue line is the surface. So with SDFs, we are storing the distance value to the surface, and when we create smoke or density, these will all store simple float values that specify the amount of density any voxel can have. And in both cases, the values that we store are float values, so these only have one dimension, and the volumes that we create based on float values are called scalar fields. So the density and SDF volumes are both scalar fields. Now, if we want to create some sort of movement, we will have to store a vector value that has both magnitude and direction. And now this new type of volume will become a vector field. So in a smoke simulation, for example, we can move the smoke around by this vector field. So any given voxel will have this vector information, and the direction will specify in which direction our smoke should move, and the magnitude will specify how far along we should push the smoke. So this is essentially the strength of a vector. And typically with vector fields, we use them to describe a velocity. So more commonly, you will find them described as velocity fields. So most tutorials and most people will refer to this field as a velocity field. So this is how I'll also refer to them in this lesson. Now in Houdini, volumes or VDBs will be split into two big categories, which is fog volume and SDF volume. And this is because SDF is a special type of volume, so we have to specify this from the start, if it's SDF or fog. So fog volume or SDF volumes are going to be the class of the volume. Now for fog volume so far, we've only been working with float values, so this is how we create density or temperature fields or any scalar field for that matter. The vector field is also a fog volume type, so these both are part of the fog volume class, and again, these are called types. And with vector fields, we can go one level below, and we also have vector types. So we can also store color information inside a volume. And because the color is made up of three components, this is also a vector. So R, G, and B are the three components, and this is why it's also a vector, but this type can't hold direction as well, and this is why we have this separate type for velocity vector, which also stores both direction again and also magnitude. And float values can only be float, so there's no other types here. Now don't worry about all of this too much for now. You'll get used to all of this pretty quickly. All of this is to illustrate that if we want to create a velocity vector, we need to create a volume. We need to set the class to fog volume. Then the type of the fog volume will have to be a vector type, and the vector type will be velocity. So back in Houdini, when we do a VDB from polygons, this distance VDB option will automatically set our volume to an SDF class, which again has no other types. And when we turn our volume into a fog VDB, this will set our class to a fog volume, but it will be automatically set to the float type. So this is what happens when we turn on the fog volume option in the VDB from polygons. And we see that here we don't have a third option to create our velocity field. So usually with velocity fields, we have to create these from scratch. So to create this volume, we can drop down a simple VDB node, and here we can specify what type of volume we want to create. So we can give this a name, and typically for velocity fields, you'll often find the name being used as vel, like this. And now we can specify the class, and we can see that the default here is going to be this fog volume. And if we do a drop down here, we don't really see our SDF class. And this is because the official name for the SDF volume is level set. So for all intents and purposes, this level set is the SDF volume. Now there's also other and staggered vectored field, and really I've no idea what these are. 99% of cases it's either going to be a level set, so an SDF, or a fog volume. Staggered vector field sounds like something we need because it has this vector field in the name, and I'm sure it's useful in some cases, but I've honestly no idea what it does, so just ignore this for now. So back to our velocity field, we'll need a fog volume, and the type here we will set to vector float. And we can see that in between float and vector float, we also have bool integer, vector integer. But again, in 99% of cases, it's either going to be float or vector float. And now we need to specify the vector type. So if we go back to our drawing here, this can either be color or velocity. So if we go back, by default, we'll have this tuple color UVW option here. So this is going to be mostly used for color. And this is again a vector that doesn't have a direction. It only has magnitude. So here we will have to set this to displacement, velocity, acceleration. And this is the vector type that we need that also has direction. Again, we have some more vector types here, but mostly it's either going to be this velocity or the color option. So let's set this back to displacement, velocity, acceleration. We can also specify here an initial direction, and let's set the display to our VDB. So if I set the background value, let's set this first value to 1. So this will just be a vector points in our x direction. So it's going to be 1, 0, and 0. And we can also specify a voxel size here. So if I want to increase the resolution, we can see that nothing happens in our viewport if we just have this simple VDB node. And this is because this VDB node essentially just creates an empty container that only specifies what kind of volume we want to create. To actually create the volume, we'll have to pair this up with a VDB activate node. And we can see here we have VDB activate SDF, so this will only work on SDF volumes, and the regular VDB activate will work on a fog volume. So let's use this version instead, and I will plug this here. Let's set the display to this, and if I increase the size now, we can start to see something in our viewport. We can specify the size here, and we can also move this around. But typically what you will do is use a geometry to base this volume on. So I will just drop down a simple box in our scene, and I will plug this as our second input for the VDB activate, and I will set the mode here to reference. So now it's going to grab the box geometry that we created. So if I select this and press enter, I can increase the size of our box and our volume will follow this geometry. And it's important to note that this VDB activate is going to use the bounding box of the geometry. So if I drop down a rubber toy and use this in my VDB to activate, it's going to use the bounding box of our geometry. So unlike the VDB from polygons, it's not going to follow the surface of the geometry, it's going to use the bounding box. And this is actually good for velocity fields because a lot of times we need this extra information around the geometry. So if we can imagine a smoke simulation that flies around our rubber toy, if the smoke gets pushed too much further out from the surface, we'll need the surrounding voxels to actually have information so we can push our smoke back to the surface. So usually with velocity fields, you'll need to cover a bigger area. Now this is tied to the bounding box of the geometry, but if we want to expand this region, we can do another VDB activate node. So let's drop down a second VDB activate and I can set the mode here to expand. And this will increase or decrease our region. And it's pretty much the same thing we did with our VDB from polygons. So over here, where we have the exterior band and interior band voxels, this simply adds more rows and columns of voxels around our existing voxels. So this is the same thing that happens with our VDB activate when we use this expand option. And we can also just use the expand distance instead. So this is my preferred way of using this option because this is tied to the world units in the same way that it works with the VDB from polygons. So let's get rid of the second VDB activate and I'll switch my input here back to our box and get rid of my rubber toy. Now, going back to our velocity field, we can see right away that even though we created a vector field, we still see this displayed as density in the viewport, and this is because they're both of the same class, which is fog volume. So if we want to preview our velocity, we can scatter some points inside this volume, and I will use the box for our scatter. So from the box, let's do a points from volume. And this will fill up our entire box with points, and we can increase the point separations here. We don't need quite as many points. And then I'll plug these points inside a volume trail node and point the second input of this volume trail to our velocity volume. So if I plug this here, if I preview the result, this will create a trail of our points that go in the direction of our velocity. So we can kind of see this vector points in our x direction, which is the value that we set over here, this background value. And this is a better way to visualize the velocity field. So we can go back here and I can decrease the amount of points. So maybe we don't need as many to get an idea on how this looks. And now we can actually start having some fun, and let's see how we can use volume VOPs to modify our velocity field. I'll just add a null in between our volume and the volume trail to keep things a little bit more organized. So let's maybe drop this down, and this will be my velocity field. So in between here, we can do a volume VOP and append this after the VDB activate. And let's dive inside. Now, same deal here, we have this bind to density by default. We can get rid of this, and to change the velocity field, we'll have to do a bind export, and we'll set this name here to our field, which is vel. We also have to specify that this is a tree float vector type, or otherwise we won't get the correct result. So we already have an initial value that points along our x direction, but we can override this. So if I just drop down a constant node, I can set this to a tree float also. Let's plug this here, and I can use these values now to control our field. So I can give this some direction in the x dimension, and we can play around with these settings, and hopefully we can kind of see the way our trails change. It's not super noticeable what we are doing so far, so let's modify this further. Now, this should not be a surprise to you at this point, but one of the main ways we can modify velocity is to add noise. So from our position, we'll generate a turbulent noise. And the signature here has to be a 3D noise because, again, we are working with vectors. So let's add our noise values to our constant. And now we can start to see something a little bit more interesting. If we go to the turbulent noise, I can increase the amplitude and we can see how this changes our trails. I can play around with the frequency. I can also animate this noise. So sort of the same operations that we usually do with noise. Let's maybe go up and I'll go to my points from volume and I might want to use less points. And we can also go in the volume trail here and we can reduce the trail length. So maybe this is a little bit more easier to see the velocity field now. This volume trail here doesn't modify the velocity field in any way. This is simply for us to visualize our field. Now, one of the main ways we are using velocity fields is to push a smoke or a particle simulation. And for this example, I'll just set up a simple particle simulation. I'll do a very basic setup and won't go too much into deal with it. I will probably have an intro to particle course dedicated specifically to particle simulations. So for now, we'll just do something simple to demonstrate how the velocity field works. Let's drop down a simple sphere because we will need a geometry to source our particles. So let's take a look at our sphere and I will also template the volume trail. So with this node selected, I'll press E. And now in my sphere, I can turn down the uniform scale maybe a little bit and I will just position this slightly to the side and maybe something like this. Now, it's important that the particles that you want to affect are inside the velocity field as far as the position is concerned. So from our sphere, we can do a pop network. Let's plug this here and let's step inside. So if I press play, we can see that now we are spawning more particles on each frame. And after our pop source, and again, let's not worry about what all of these nodes do. This will be a separate course dedicated for particles. After our pop source, let's do a pop advect by volume. So let's drop this over here and we have to specify a velocity field in this subpath so I can go up and I can grab this velocity field. So this null over here and I'll press Ctrl C. Let's go back inside and let's paste this in our subpath. And now this will grab the path to this velocity field. And if I reset the timeline now and I press play, we can see that the particles are moving in the direction of our velocity field. Now, there are quite a few settings here, and again, I will cover all of these settings more in depth in the particle course, but for now, let's just set the advection type here to update velocity, since we will get a more accurate movement in relation to this velocity field. So if I reset the simulation and press play, now our particles are moving a little bit faster. And we can see this weird thing happening here, which is that when our particles are escaping the velocity field, so if I go up, we can also preview our trails. And this is the entire bounding box of our velocity field. So when they are pushed upwards and they escape the velocity field, they no longer get this vector information that we have over here, and they're just sliding along the surface. So this is obviously not what we want, and we can go back to our box over here that determines the size of our volume, and if I press enter, I can increase the size here and increase our field. So now if I go back to the particles and reset the simulation, if I press play now, we have a little bit more space to advect our particles, but obviously here we can still see that they reach a certain point when they no longer find any voxel information. Okay, so we do this sliding. So this is why I said earlier that with velocity fields it's usually better to have more voxels surrounding the regions that we want to simulate. Now, to fix this, we can just change this velocity field. So if we go inside the volume VOP, let's just change the direction and let's just make this vector our initial direction point only in the x direction. So I'll set the value here to 1, 0, and 0. And this is our new field now. And also for our noise, we should have said this from the beginning. Let's change the noise type to simplex noise. So now the pattern, the noise values will be applied in all directions. So if I increase the amplitude now, we can kind of see the result we get. So if I go up and I reset the simulation, let's take a look. Okay, so we can kind of see these particles as they move along our trails. And we can probably no longer need to visualize this volume trail, so I can press E on this to get rid of the template flag display, and let's just focus on our PubNet simulation. So I can press play and they will travel along our velocity field, and over here at some point they're going to reach the bounds, as we can see, and basically they keep moving forward because they will maintain the last velocity that they registered while they were inside of the velocity field. So this is why they keep moving. We don't really have to worry about this. Typically, when you will create a velocity field, you will more than likely take into account the path that you want the particles to take and adjust the velocity field accordingly. So if I go back to my volume VOP and I animate this noise, let's maybe just right click and choose to promote input parameters. I'll go up and let's just preview the volume trails. I can animate this noise by animating the offset value here. So if I animate the first value, let's set this to a $T expression. And if I press play, we can see that the noise kind of has this swimming pattern to it. And this will also translate to our particle simulation. So if I go to the PubNet now and press play, now we will have a much more organic result and the particle, or rather the simulation, feels more alive. So if I change the offset value here, let's go ahead and multiply this to make this faster. So let's multiply this by 3 maybe. Let's reset, and now we can see that they're even faster. So now it's actually starting to look like a fluid simulation. So hopefully now you can kind of get an idea on how these velocity fields work. Now, obviously, this velocity field that we set up here is just a very basic vector volume, so we can get really a lot more advanced with this. And inside the volume VOP, we have access to all of our VOP nodes, and we can use geometry for the outside to direct how we want the velocity to be, and we can combine it with other volumes as well, and we can also use SDFs. So there's really a lot of stuff that we can do. Let's do a more practical example and try to create a velocity field based on a curve. So I'll drop down a curve sub from here. I'll set the primitive type to NURBS curve. Let's go to our curve and I'll hold down spacebar and press 2 to go in the top view. And let's just draw this curve maybe across a span of 4 units. So from -2 to a value of 2. I'll press enter in the viewport and let's just draw a simple curve. Let's do maybe something like this. I'll press spacebar 1 to go in the perspective. I'll press F to go into editing, and I might just want to also make this more of a 3D curve. So just try to have a more interesting path here. This doesn't really matter this much for this example, so let's just do something like this. I think this will be fine. Now, because this is a NURBS curve, it doesn't have any usable geometry, so we usually pair this with a resample node. So let's drop down a resample, and now if I turn on the point display, we have regular geometry that we can use, and we can store attributes now on these points. Now, earlier I said that usually to create a velocity volume, we start with a simple VDB node and create an empty volume first, and then use VDB activate to set the size and all of that stuff. But we can also just base this velocity volume on an existing fog volume. So I want to give this curve some thickness, and we can use a sweep node for this. So let's drop this here. I'll set the surface shape here to, let's do round tube, and now we can increase the radius to thicken this geometry, and we can also increase the resolution, so give this more columns, and something like this will be fine. And now with this geometry we can use our good old VDB from polygons. So let's drop down a VDB from polygons from here, and if I increase the voxel size, we can see something weird happening in our viewport. And this is one point that I forgot to touch on earlier. In order to turn geometry to volumes, we need to have closed geometry. So over here we can see that on both ends we have these holes in the geometry, And to fix this with the sweep node, we can scroll down here and let's go to end caps, and we'll set the end cap type. Let's do single polygon. So now we have closed off this geometry, and if we go back to the VDB from polygons, we can see we get the expected result. So I can increase the resolution here and everything works as expected. So keep in mind, if you are using this VDB from polygon and you don't have the expected results, this usually means that the geometry is not closed off. So from here, we need a fog VDB. So if we go back to our graph, the velocity field is a fog volume class. So let's go back here and I'll just turn on fog VDB and turn off the distance VDB. Now, if I look at the information here, this by default will give us the regular float type of fog volume. So again, if we go back here, this is the default that our VDB from polygons will do. And we need a way to turn it into this vector type. So from here, we can do a convert VDB, and we will convert to, by default this is set to volume, but let's say convert to VDB, which it already is. But now we have access to our class and the type as well. So for class, we already have what we need, which is a fog volume. We can see that we can actually convert fog to SDF, and we can also do the other way around. So if we were working with a SDF here, so if I turn this to surface just for demonstration, if I go back here, we can do convert SDF to fog. So this is also very useful as well. Let's just do our regular fog VDB, and here we will say no change. And now for our VDB type, we actually want a vector float. Now, we don't have a visual representation in our viewport that this changes, but if I go to the information here, we can see now that the voxels store a vector information. So previously over here where it says vec3s, this was float. So now our density VDB is actually a vector volume. And on this note, we can change this density name. We can go to our VDB from polygons and let's just name this to vel. Again, you can use whatever name you want here, but usually Houdini will look by default for this vel name when we are doing a pyro simulation or other operations down the line. You might also find velocity volumes named as V, so sometimes it's just a simple V, and this is also how some of the Houdini nodes are configured to look for a volume that's named V, but I'll just keep this at vel, and we can move forward from here. So what I want to do is give this velocity field a direction that goes along the curve. And what we can do is create this direction as an attribute on our curve geometry and then use a volume VOP on our velocity field to sort of borrow this attribute from the geometry. So from our resample over here, I'll just drag all of this to the side. Let's go to our resample where we have the points on the geometry. We can do a polyframe from here. So let's drop down a polyframe. And here we have this tangent option, which will give us a vector that points from one point to the next point. And this will create this direction that we want. And I'll turn off this normal name. And instead of the tangent name, tangent U, I'll just name this dir for direction. And if we go to the information tab and let's create a visualizer for this, here we can preview the direction of our vector. So this is what we want. Let's turn this off. And from our velocity field, let's do a volume VOP. Let's connect this here to our field. And we want to reference our curve geometry. So from this polyframe, let's plug the polyframe node as the second input in this volume VOP. And let's step inside. So in order to grab this dir attribute from the geometry, we can open a point cloud on our curve geometry. So from op input 2, which again references this curve, let's do a PC open. So point cloud open. So this PC open we talked about in the intro to VOP series, but I'll try to explain this again in relation to volume. So here I have a cross section of our volume, and let's imagine that this grid represents our voxels. And here we have, let's say that this green line represents our geometry. And because we created this volume with a VDB from polygons, in reality, we sort of have a border that looks something like this. So this red outline. So it's not a box container as it was in our first example when we created the velocity field using the simple VDB node. Now again, this will depend on the effects you're trying to create. A lot of times you might want the full box container, and sometimes you can get away with less voxels, such as this case. So the PC Open will open a point cloud from the position of each voxel. And again, this will be a point that lives right in the center of each voxel. And for example, for this point, it's going to open a search radius. And this search radius needs to be big enough to contain the points of our geometry. So I have to set the search radius to a high enough value until it reaches the actual geometry. So something like this. And this will be in world units. And we'll see this in action in a second. And now that the search radius can contain the points of our geometry, of our curve, let's say that it found maybe these 4 points on our geometry, we can also specify the total number of points that we want to consider. So for example, even if the search radius is big enough, we can limit this to only select 2 of the points that it finds first. So usually the less points we search for, the faster this operation will be. So that's also something to keep in mind, but let's go back to our example. So let's say that we found 4 points. Now we can grab attributes from these. And if we want to grab the position attribute, we will return the average of the position of all of these points. So in this case, we might return a position value that's maybe somewhere around here. So an average between all of these positions. And then we will do this for all of the voxels at the same time. So we open up a search radius. So for this voxel, for example, we find all of these points over here. And the average of these might be a point that's somewhere around here. And for this point, the average of the points might be here. And for this one, we might return this. Now we can grab any attribute. It doesn't necessarily have to be position. So if we had a float value on our curve geometry that we want to average, and let's say this float value might be a value of 2 for this one, 1.5 for this point, and 1 over here. The average of these points will return us a value of 1.5, so we can also grab any attribute that we want. And in our case, we will return the dir attribute, so the vector that points along the curve. And this averaging here of the values usually will provide us with very nice and smooth results, and this is constantly used in simulations. So if we go back in Houdini, the file on this PC Open will simply specify which geometry we want to consider. So again, this will be our curve geometry. We want to open the point cloud from the position of our voxel. So we will plug the P inside the P here. And then here we have the search radius and the number of points. So again, the search radius we will have to increase far enough for the voxels to reach our curve geometry. So I'll just set this to an initial value. We'll have to preview the velocity field in a second to actually see this in action. And again, the number of points specify how many we want to consider. So we actually don't really need to average out 10 points. In this case, after maybe averaging 5 points, we can get a pretty accurate estimation. So considering more points in our averaging operation doesn't really give us a better result. Maybe I'll just set this to a number of points 5, and we can always just increase this if we find that we're not getting the most accurate results. Again, the search radius and the number of points kind of go hand in hand. And for both values, we want to use the absolute minimum necessary to get our results. The more we increase the search radius and the number of points, the slower the operation will be. And now to get the attribute that we want from our handle, we will do a PC filter, and this is what will average out the attribute that we need. So in this case, it's set to the position by default, and we said that we want to grab the dir attribute. And the signature here will be a vector channel, so we'll leave this as it is. Let's do now a bind export to our volume, and let's export this back to our val field, and let's set the type here to 3 floats, and here we don't need the density. So again, we are previewing this as a fog volume, and this is not useful. Let's go up. Let's do a null from here, and this will be our val. And again, we will use a volume trail. So from our sweep over here, let's scatter points inside this geometry. We will do a points from volume. Let's maybe give this a point separation of 0.2. and we can plug this in a volume trail node as the first input, and we will plug the velocity volume as our second input. So now let's see what we get. And we kind of see now this vector in action. And now I can go back to our PC Open values over here, and we can see, for example, if I were to decrease the search radius, we no longer get the information that we need on the voxels that are further outside. So if we go back to our graph, these voxels that are further away from the geometry don't have a search radius that's big enough to actually find the points on our geometry in order to retrieve the attribute that we want. So this is why the search radius needs to be big enough. So I'll just increase this until each voxel can find points on the curved geometry. So maybe somewhere at around 0.5 will be okay in this case. And if I increase the number of points here, we can see that we get the same result when I increase this, but if we have too few points, we might not get the correct result. We can see that in this case, even with 1 point, we get a pretty good result. Let's just set this to a value of 5 and keep this, or maybe let's just use 4. So we can now see this in action. So if I go up, we can go back to our setup with the particles. So let's grab our sphere. Let's maybe just template the volume trail with E. I'll go to my sphere and let's press enter, and I just want to move this to the end of our sphere. So let's just move this up, and we have to make sure again that this is actually fully inside our velocity field. So let's do something like this, and I might want to reduce the uniform scale a little bit. So now if I grab this velocity, so let's grab this null node, press Ctrl C, and we'll replace the SOP path inside the POP network over here. For the pop vect by volumes, we will replace the SOP path with our new velocity. So let's press enter. And now if I simulate, we can see that the points are going in the opposite direction. So to reverse the direction of our vector, we can go back inside our volume VOP. Let's maybe just preview the volume trail. So if we go inside the volume VOP, to reverse this direction, we can do a negate here, which just multiplies the vector with a value of -1. So now if I go up, our points should be going in the correct direction. So let's press play. And now we can see that we are following this velocity volume, and we can also preview our trails, and this is the result. Now, naturally, when they escape our field, they stop moving, and this is usually fixed if we make our particles die off when they reach this point, or we can create lots of different logic that simply removes the particles when they reach a certain point, or we might have a camera in our scene that doesn't even capture this part. So this is just standard Houdini stuff. Now, obviously, to make this more interesting, we can introduce some noise. So back in our volume VOP, let's do a curl noise of this time. So we will do a vector to vector 4, and the curl noise can use 4 values, and we'll use the 4th dimension here. We'll plug this into our time so we can animate this noise, and from here we'll do a curl noise. Let's set the type to simplex, and we will add this to our velocity. So after the negate here, we'll drop down and add, and let's plug this over here. And we can already see this change in our viewport. So let's right click and choose to promote input parameters. So now we can go up. Let's just preview our volume trails. And by default, if I play, this will also have animation. And this 4th dimension in the frequency is what's going to determine the speed of this. So if I grab this 4th value here and I decrease the amount, we can see our noise animating slower. So maybe I'll use a value of 0.1 in this case. We can increase the amplitude, and we can play around with the offset as well. So let's see now what result we'll get in our simulation, and let's press play. All right, now the amplitude might be a little bit too strong, and we can see again when they escape here, the velocity field on the borders, they stop moving entirely, but they kind of maintain this direction. I might want to decrease the amplitude here. Let's use 0.4 maybe. All right, so this is more like it, and we can see we have this nice fluid kind of animation. Really here, sky is the limit as far as modifying this volume is concerned. So let's say, for example, we can see that as the particles progress further through this velocity field, they start to get a little bit more chaotic. And let's say that we also want to push the particles towards our curve as they progress. So back to our volume trails, we can grab the position of our curve and generate a vector from the position of each voxel to this position on the curve. So back in our volume VOP, again, from our PC open, we can do another PC filter. So I'll hold Alt to duplicate this, and we will use the position as our channel. So on the points that we find over here, we will average their position. And when we grab the position of each point, so something like this, if we subtract the position of the voxel with this position that we find, we create a vector that points towards the curve. So for this voxel, we subtract the position with what position it finds with the PC open, and we have this one, and then in this case, we'll have this vector. So this is what's going to help us push the particles back towards the curve. So let's go back here, and with this PC filter, we grab the position and we will subtract the position of the voxel. So let's do a subtract from here. Let's plug the PC filter as the second input, and we will just simply add this result to our velocity, and we can kind of see this happening here. We can also scale this vector if we do a multiply after the subtract, and I want to promote the second input here. Let's maybe rename this to push back, so it's clear what this does. And if I go up, as I increase this value now, we can see how our vector field changes. And I think this has to go in the opposite direction. Right now as it is, I think it's actually pushing it further away from the geometry. Okay, so this is what it does. So let's reverse this direction of this vector. We can step back inside and we can simply reverse the order of subtraction here. So I'll grab this node, press Shift R, and now we have the actual vector that we need. So if I go up, we can see now how this vector field points towards the curve. So let's just give this something like 0.5 and let's see the result now. So let's press play. And now over time, as our simulation progresses, we can see that it travels further and further closer to the geometry. So now I can go back here and I can increase the amplitude of our noise, and maybe I can decrease this pushing back vector, and let's press play, and we can start having a lot of fun with this now. So now we also don't run into that problem of the particles escaping the velocity field. And as I play around with some of the settings, we can get some really cool results. We can also animate this noise faster, so I can increase the fourth value here, and this is the result that we get. So we can see it's a nice and smooth animation, and it follows our curve pretty closely, so we can really do a lot of this. And here I'm just barely scratching the surface. Now, so far we've been using mostly geometry that has polygons to create volumes based on the geometry, but we can also turn geometry that only has points into volumes. So if I create a simple point here, I'll drop down and add, click this plus button here, and this will create a point in the center. If we want to turn this into a volume, we can use a VDB from particles. So let's drop this here and append this. And this will create a sphere volume based on our points. And here we have a few settings. So first of all, we have the usual voxel size that determines the amount of voxels that we have. Then we can either create an SDF or distance VDB, and we can also just create a fog VDB like so. There's also this mask VDB option, but this honestly doesn't come up that often. Don't worry about this for now. We have our two main classes, so the fog VDB and the SDF or distance VDB. Let's just keep this as an SDF for now and check some of the other settings. Point radius scale determines how big we'll draw our volume in our scene, so we can control the size of this volume. Now, if we have more points, this will be applied to all of the points. And minimum radius in voxels determines how many voxels a point needs to cover in order for it to be drawn. So if we go back to our cross section here, if we look at this voxel here, let's say that there's a point, the blue dot. Let's say that we have this point that's right in the center of the voxel. Now, it doesn't necessarily have to be in the center of the voxel. Let's just say that this is in the center just for the sake of demonstration. If the radius that we set for our points doesn't cover this, let's say 1.5 span of voxels, then it won't get drawn. So we can see here that it covers this whole voxel, and maybe it covers at least half of the voxel next to it. So if this radius wasn't big enough, so if this was smaller to maybe 1.2, it will no longer get drawn. So this needs to be at least covering 1.5 voxels around the point. So back in Houdini, if we have a voxel size of 0.1, if we set this point radius scale here to 0.1 as well, it will perfectly fit only one voxel, so it will look something like this. So now this minimum radius will ignore this point. But when the scale goes above 1.5, so if I increase this, when we go above 0.15, so to 0.16, now this condition is met and we can draw our SDF in the viewport. Now, this value of 1.5 is what Houdini recommends, that the point should at least cover 1.5 voxels to not get artifacts, but a lot of times I reduce this minimum radius scale to match the size that I'm using. So if I were in fact using a point radius scale of 0.5, I can just reduce this until we get our volumes working. So I wouldn't worry too much about this size over here, to be honest. If your volume gets some really nasty artifacts, this setting here is something that you should look into, but generally I have set this to a lower size and I got the results that I wanted. Let's reset these values for now. Now the point radius scale here is really just a multiplier of a p-scale attribute that exists on the points. Now if our point in this case doesn't have a p-scale attribute, Houdini will assume a p-scale value of 1 if this doesn't exist. So if I set this back to a value of 1 for the point radius scale, if on my point I add a p-scale attribute, so let's drop down an attribute create, I can create a p-scale attribute, so I'll set the name here to p-scale, and I'll just set the value here. Let's maybe leave the value at 0, and if I go to the VDB from particles, now if I increase the p-scale value, so if I scroll this up, we can see that this changes the size of our volume, so I can increase this and decrease this, and now if I go back to the VDB from particles, this radius scale, like I said, will act as a multiplier, so I can still control the size using this option instead. So whether you want to adjust the size directly on the points with the p-scale, or you want to control the size here directly, this will be up to you. They both will do the same thing. And usually we want to turn points into SDF volumes when we are meshing liquid simulations. So let's see how this works on our previous example here. I will set the p-scale attribute in this attribute create. Let's set this value to 0.1 and I will connect this to our POPNet. So I'll drag these to the side. Let's look at our result in the VDB from particles. So we can see nothing happened, and this is because our point radius scale is too small. So as I increase this, we should start to match the conditions that we need. So we probably need to go above 1.5 because we have this p-scale value here of 0.1. So when I go above 1.5, we can start to see this now. So if we had the same value that we had before, so if I drop this point radius scale to 0.25, I can also increase the amount of voxels we have until we find the right value to create our volume. So if I reduce the voxel size here, I will hold down shift and use my scroll wheel to go down. We can reach a value, we can see 0.01 in this case, where we have enough voxels so that this point radius scale will match this condition. So if we go back to our cross section, if we look at this voxel here, our point scale, this radius here, this will stay the same. But when we introduce more voxels, we are actually dividing up the grid like this. So let's create maybe one more division. Now we can see that the radius actually covers maybe 2.5 voxels since we divide this. So this condition here, minimum radius will be matched, even though the point radius scale will stay the same. So all of these values, voxel size, point radius scale, and minimum radius are all very tightly linked with each other. And all of these usually require some finessing to get the correct result. Now we have a pretty okay resolution for our volumes. And with more voxels, we can get away with a lower radius scale. So I might want to reduce this, and we can see we reach this 0.5, this 0.15 value here, where we call our points. Again, I can set this to a lower value and just reduce the minimum radius, but let's keep this at 1.5 and just set the radius scale to the lowest value that we can possibly use. And now to turn this SDF into actual geometry, we can do a convert VDB, and we'll set this to polygons. All right, so here we have it. And the power of the SDF is that we can use all sorts of SDF operations. So after we turn our points into SDF, we can use a VDB smooth SDF. And I will decrease the iterations here, and we can use different algorithms to see what kind of results that we get. And usually with fluid, I think this mean curvature flow is what's generally used. So we can go back to our geometry result. And after the VDB is smooth, I can also do a VDB reshape SDF, and we can push this volume out, or we can erode it, so we can eat away parts of our volume, we can squeeze our mesh. I can place this VDB reshape before our smooth, for example, and I can dilate this, so I can push this out like this, then I can smooth this out, so I can increase the iteration, and I can combine this with another VDB reshape SDF, set this to erode. All right, so now we can see how easily it was to smooth out this result. So if I disable all of these nodes, we can see that this was the initial result where we just turn the points into volumes. And when we do all of these operations, now we get this nice liquid kind of mesh. So hopefully this gives you an idea on how to mesh particles, and there's really a lot of things to consider when you want to mesh fluids, and there's a whole art to it really. Fluid meshing probably has its own fan base, but at its core it's really just turning the points into an SDF volume, then doing multiple operations on volumes, and also optimizing the points themselves before you turn them into volumes. Now, like I mentioned before, we can either turn the points into an SDF or we can turn them into a fog volume like so. But there is a better way to use the fog volume version, and this is by using a volume Rasterize attributes node. So let's drop this down over here, and we kind of have some of the settings that we are used to. We have the voxel size and the particle scale. So this particle scale here will also act as a multiplier, kind of like it does over here in the VDB from particle nodes. Let's go ahead and just duplicate the attribute create node, which has our p scale value. And the way the volume rasterize works is that it's going to look for an attribute and base the density or whatever kind of volume we want to create on that attribute. So this is why we don't have anything currently showing, because we have to specify which attribute we want to rasterize. So over here we have all of these attributes that we get from our PopNet simulation, but let's go ahead and just create a simple density attribute that has a value of 1 over all of the points. So in our attribute create, I will hit this plus to add another attribute. I will set the name here to density, and I will just give this a value of 1. And now in our volume rasterize attributes, we can specify the attribute here. Let's type density. And now we can see our fog volume, and we can increase the voxel size here, so we can reduce this. And in the case for the volume rasterize attributes, we don't have to worry about meeting this minimum radius in voxel threshold. This option here is more when we are dealing with SDFs, to be honest. So in our rasterize attributes, we don't have to worry about this. And I can set this to, let's set this to a lower size, so 0.01, to have a lot of voxel information. And now again, we have a p-scale attribute on our points, and this particle scale here will act as a multiplier. This minimum filter size here is honestly something that you should just leave as it is. We can see that as I change this, nothing really happens. There are a few cases where you might want to change this filter size, and this again is a way for Houdini to kind of fix artifacts between voxel interpolation, but you really shouldn't worry about this option for now. So let's leave the particle scale at 0.5 for now, and we can see that we essentially now have a smoke simulation. So we can render this now as a volume instead of particles, and this is how a lot of magical effects are created. We create a particle simulation and then we render those as a volume. And the cool thing here is that we have this velocity blur option. So if we go to our points, we have velocity on all of our points that we got from our particle simulation. And this volume rasterize velocity blur option will smear the density along these velocities from our points. So when I turn on velocity blur, we can kind of see something happening. And if I go to the settings here, I can increase the shutter, so this will smear the density even more, and we can also give this more samples, which will increase the quality. And the shutter offset specifies in which direction we should smear, and generally we should set this to a -1 value, so we can smear the voxels backwards, because it makes more sense in a simulation. We want to trail backwards from our position. So we can see as I change this shutter offset from 1 to -1, our voxels are kind of going backwards a little bit. Now, this isn't really the highest quality result, and even if we decrease the voxel size here, so we use a grid that's twice as big, we still didn't improve this quality. And if I decrease the voxel size, we can probably set the particle scale to a lower value as well. And if I set this to a lower value, here we can see now better this velocity blur in action. So when I turn this on and off, we can see how all of the voxels are now smeared in this velocity direction from the points. So this is super helpful, especially when rendering. And usually when we want to turn the particles into smoke, we need to be working with a lot more points. So in the particle simulation, I'll just go here for my pop source, and in the birth tab, I'll increase the constant birth rate. Let's add 10 times more particles, so I'll add another 0 here, and let's go to the simulation and resimulate. So now essentially the more points we have that can be contained within a voxel, the better and smoother result we will have. So in our volume rasterize attributes, we see now a much smoother result, and with more points we can lower the voxel size, so I can go even lower now to get a better result, and I can decrease the particle scale even more. So if I set this to 0.1, now we can see we get very nice smooth results, and this velocity blur we can really see it now in action. So this is already looking pretty cool. So we are rasterizing this density attribute from our points, and currently our density has a value of 1 across all of our points, but we can use different values per each point. So if I use an attribute noise float, let's set this over here and let's change our density. I'll set the operation for the noise. Let's multiply this, ranges 0 centered, and let's also preview this. If I click on this icon over here, we can see the values of our noise, and maybe we can enable ramp so we can further control this, and I can increase the amplitude. So now the red values will have the full density, and these violet areas will have no density. So when we go to the volume rasterize attributes, here we can see these gaps in our density. We still have voxels here, they just have a density of 0, so it kind of looks like the volume is empty on these sides, and it has a full density value over here. Again, if we go to our points, we can see the pattern that our noise creates. So previously, when we didn't have this noise on our density, we had this result, and with noise now we have this. So this is also one of the strengths of the volume rasterize attributes, because the attributes will usually have different values per point. This volume will use all of that information, and we don't necessarily need to rasterize only the density. We can add as many attributes as we want here. So because our particles have points, we can also rasterize the velocity attribute. So if I add here v to this list, now we also have a velocity field. So if I go to the information here, we have the density, which is this float value, and we have our v, which is a vector 3 types. So we can very simply create a velocity field with this volume rasterize as well. And this comes up in a lot of cases. So if I want to preview this velocity field, let's go to our points, and I don't really want to trail 200,000 points. So what we can do here is simply merge the points that are close to each other. Let's drop down from our popnet, we'll do a fuse, and we will just increase this snap distance, and we can see that as I increase this, it will simply average all of the points and merge the points that are close to each other. So now we have only 3000 points, and we can do a volume volume trail from here. Let's plug the volume rasterize as the second input, and let's look at our trails to preview this velocity field. Here we don't have the correct result. It's going to grab the density volume to trail the points, which doesn't make any sense. So when we have multiple volumes on any given object, here for the volume trail, we actually have to specify the velocity volume ourselves. So let's point this to the V volume. And now we can see our velocity field. So we are turning the points into volumes, and then we are storing the information from the points inside those voxels, and in this case we are storing the density, and this can be used for shading, and we are also storing the velocity if we further want to use this as a velocity field later. So essentially with this velocity field I can use this to push out smoke or another particle simulation, and over here where we created our initial volume velocity using the regular VDB node, we could use the box container to scatter points, and then we could have created a velocity attribute on all of these points, and then use the volume rasterize attributes to turn this into the velocity field, so to have this result. So whether you want to use geometry or points to create volumes will be up to you, and it will depend on a case-by-case basis. And you might find a lot of tutorials that use the volume rasterize method instead. So some people prefer to just work on points to get the directions that they need, so the velocity attribute. And essentially in this volume VOP here, where we decided how our velocity field should work, all of these operations, if we just simply add all of these to our points inside an attribute VOP, we can then rasterize the points and we get sort of the same result. Usually for velocity field, like I said, I like to create the volume from scratch, but there are cases where you might want to use points instead and rasterize those to create the volumes.